It's okay. Just do your best. Do your best. I can take over anytime.
Whenever you guys are ready. 10 minutes.
I'll just check this works. All right, good. Okay, hey, I am Akil Gunasekaran, and
I'm Jefferson. Good evening.
yeah, so we're both freshmen here at UCSC, and this presentation I'm about to do today is a part of a larger research project with Professor Jason Asragian on continuing learning using spiking neural networks. So this is just something we kind of put together to see like how the training would work in a continual setting. So we will present now. So in the beginning, I want to go over just regular neural networks and specifically how they're trained. So regular neural networks, at least pretty much most popular neural networks, VG16, transformers, all those things use batches. So batch learning means that we take a small subset of the total training data and we feed that into the network. So usually batch sizes can be like a size 128. And we take that 128 samples from the total data set and we feed it into the network. And we do that many, many times. And that's how the network learns. However, the issue is that when we have such a large batch size, the network sees data points more than once. So that means that multiple images, for example, like in this case where we're doing MNIST, multiple images will be seen multiple times. However, there might be scenarios where we only want images to be seen once, such as a continuous scenario where images are coming in one at a time, and we don't have like one full data set to kind of train from. So in addition to this, the training of traditional neural networks are very time consuming, and they are a lot of weights, and this is very computationally expensive. So this is like some of the downsides of using traditional neural networks with large batch sizes. So as an alternative to regular neural networks, we have spiking neural networks. So spiking neural networks use a spike to model their neurons. So essentially what these are is you can kind of think of them as basically like a spike. And then when a certain threshold is reached, that'll trigger a positive correlation. And if that threshold isn't reached, that will have a negative correlation. And it's a very simple way of modeling a neural network that doesn't have like a global loss function. So it's less computationally effective, less computationally expensive, but it is less effective in terms of the actual output. So yeah.
Okay, so once we have a brief basic understanding of how neural networks works, we need to understand how our brain works. Because eventually our goal, at least for modern day, is to make neural networks act exactly the same as our brain works, which can learning, planning, and eventually creating stuff. So in many neural networks modern days, we use a strategy called back propagation, which you go back once you get a result from a training set, and you go back and you eventually change the weight on the training set, and then. But the case is that our brain doesn't use back propagation. And one reason is that we need to learn immediately and really fast and change the weight immediately. For example, if we touch a fire, we don't touch a fire twice. Once I touch it, and for the rest of my life, I know fire is dangerous and I'm not going to touch it again. But for neural networks, lots of times, you touch it and you touch it and you touch it. Maybe you touch it 100 times, 1,000 times, and eventually oh, this fire is dangerous. But so in order to change that, we have to continue learning and update our information, or at least our training sets. And that's why we don't use ANN's artificial neural networks as our research, because ANNs use back propagations as one of the main methods. And also, another advantage why we use spiking neural networks is because, again, our brain have long-term memories and short-term memories, and we can change the weight as we receive new informations. Yeah, and again, as spiking neural networks take less energies, which as a students we don't have that much GPUs and all that stuff to process the data. Yeah. And so once we understand all this basic stuff, the method we're using is continuous learning, which again, continuous learning, you always adding new informations or adding new training sets. And because neural networks, they always have a problem, like they're prone to catastrophic forgetting, where as you're learning new informations, you forget what the old information is. So eventually you need to take lots of times or redoing like back propagations to re-enhance the weight. But for the continual learning, you're updating the informations as the things goes on, which acts more as how our brain works. And yeah, and one like real time application for this is recommender systems. So platforms such as YouTube and Netflix, they use recommender systems where once you like click on some videos or films, you don't immediately immediately update what you like. So for example, if I watch horror movie for the last 4 months, and then recently I start to watch action movies, but I don't just want to immediately change. Hey, like in the future, they always recommend me action movies. I still want to see some horrified movie. So that's where we don't forget the old informations, but while we're receiving the new informations. And that's the one application for the continual learning.
So it's also worth mentioning that although continual learning is like really, it's kind of like what the optimal scenario is, at least in terms of like what businesses would want and things like that. It is obviously very difficult for neural networks to train continually because they want lots of data, and just passing a sample one time through a network is generally not enough. And, you know, if we just keep passing in single samples, eventually what the neural network was originally trained on will kind of forget that information, and it'll only learn what it'll only like remember what it recently learned, because basically data points have a large influence on the gradients. So, you know, imagine I keep passing in new data points, and the gradients are changing all the time. Then eventually the gradients have changed so much that, you know, the old information is not represented in the latent space that well. So I'd like to talk about our model now, which is what we did today. So we used essentially something called surrogate gradient descent, which is basically a approximation of a spiking neural network that still uses gradient descent. And we used a batch size of 128. We used the optimizer, we used the atom optimizer, which is the most popular optimizer. Our loss function was cross entropy loss. And again, like I mentioned, we use surrogate gradient descent, and we have 2 fully connected layers. So it's just a 2-layer fully connected network. So our main contribution in this was the reservoir. So the reservoir is essentially, at least the way we implemented it, was basically just a list where the data point and the target was appended to the list. And during the training, approximately every 10 training cycles, it would take 5 out of the 128 samples and append them to the new list. And then every time it trained in a new batch, it would go through and iterate over all of these old samples that have been appended to the reservoir, essentially. So by doing this, it's remembering the information from prior batches, because we're taking a small subset of those batches and putting them into the reservoir. So as training continues, that information is still kept in the reservoir. So that information is being, it updates the gradients, and they're not forgetting like the old information, because that is having an influence on the gradient as time goes on. So this is our loss curve for our initial model. So this is like the plain regular model that doesn't use our system, our reservoir system. So basically a regular spiking neural network trained on MNIST. And here's our loss curve for our method, which is includes the reservoir. So it's actually quite similar. If you pay attention to the y-axis, it's actually fairly similar. So yeah, it's generally the same. We noticed across both these examples. But what is different is the actual classification. So we achieved a 0.2 bonus in the classification accuracy, which tells us that we probably need to do some more modification, and we have like future plans that will potentially have a bigger bump. For one, we had a very large batch size, 128. And in the future, we plan to kind of have smaller batch sizes and have a more realistic continual learning scenario. So that's basically what I kind of talked about in the future. So for a reservoir, at least the way that we had it, we implemented it as a Python list. That is not very good because having a lot of PyTorch tensors in a list is very computationally expensive. And it's, as if I have a large data set, it's going to be very large, like very large list. And we don't want that. So we'll use a data loader instead, a PyTorch data loader. Another thing is we'll do is put a memory capacity on the reservoir. So the reservoir stores prior samples. And what we could do is after a certain amount of tensors have been added, we pretty much just get rid of some of the old tensors. So almost like a queue, essentially. Another aspect that we are looking at is more complicated is making a time-dependent reservoir. So right now, our reservoir adds according to different steps. So after like 10 steps, it adds 5 out of 128 images. And rather than doing that, we're thinking of making it time-dependent. So spiking neural networks are, what's special about them is that they have the time dimension. And that allows us to basically potentially add images to the reservoir based on time rather than based on steps. So in addition, we have other papers that we're thinking of implementing, including dark experience replay and then gradient episodic memory and some other popular continuing learning papers that we're thinking of like adding to our model. So yeah, thank you. That is our presentation today.
Thank you very much. All right. Yeah, quickly questions.
Yeah.
You said you're storing the reservoir as a list of tensors?
Yeah.
Just like an extra dimension for the tensor?
Yeah, so pretty much it was kind of a very brute force way of doing it. So the way that the neural networks learns is just by the data is a tensor, the target is a tensor. So, and then it's pretty much just learning an association between those two because the images are compressed into tensors, right? And all we're doing is just putting it literally to a list and then it goes through the list as in, you know, yeah. Oh, yeah, you could do things like that. But again, like we said, we're using a very brute force, like simple method, which is just literally having a list that stores the data and the target tensors. And we just iterate through them consecutively together. Yeah. Yeah, obviously I mentioned also like we're thinking of using a data loader instead, like a PyTorch data loader, which would be more efficient. And it would also mean that, you know, other models could use that same data loader themselves. They don't have to implement this from scratch every time. Yeah. Any other questions? Is there like Zoom questions or anything? Okay.
Thank you very much.
Thanks.
Cool beans. Let me freeze this and we can get going again.
All right. Well, we only got one more.
Indeed we do. Or maybe, I don't know. Hey, third group. You guys, how's it going? You getting, yeah? Amazing. Yeah, Cohen's not involved. He's there for moral support. Assuredly.
They're paying me for my
100%. Yeah, that's what. Yeah. Okay. All right. On Zoom there, can you hear us? Let me see real quick.
Yeah, I can hear you guys.
Excellent. Okay, and we can hear you. That's awesome. Let me just
Okay.
turn this up a
I
little.
was a little worried about that.
Yeah, we can hear you. Hold this for a sec.
We increase it just for him.
Oh,
His volume is pretty high for just him.
please.
Use that just so like
Audio settings. Let's do speaker output level. All right, say something.
Jack, say hi. Jack, say hi.
Hello? Hello?
Say it just a little bit louder.
Hello? Oh, wait, let's see if I can. Is this a little louder?
Yeah, you're good.
Yeah, that's better. Bet.
Okay, I think I turned up my microphone.
Excellent.
right.
Screen, yeah.
Can you see the screen?
Yeah.
Sweet. All righty. Let's rock.
I'm really excited to see this stuff seems
I am too. I am very happy with our results. I was a little afraid, but when we started getting results, I was like very excited.
Very excited. You guys probably want to come over too, see spot marks.
Yeah. You guys are probably gonna want this. Can people hear me? Is this okay? Yeah. All right.
Oh, also, Kevin, I can only really hear you right now. I don't know if anyone else in our group is speaking.
We'll be passing the mic back and forth so you can
Okay,
hear the person
cool.
speaking. I am Kevin Batchelor. This is Sean Singh. This is Doc Shaw, and you should be able to hear Jack Hansen. We can't see you, but if you want to say hi.
Oh, hello.
And so our submission for the Sky is No Limit challenge for this spring is a playlist generator. And now you hit down to go next, I think.
So our project is a Spotify playlist generator that will use a Kaggle dataset to associate the song's audio data with the characteristics of the song, such as the energy and instrumentalness and many other statistics. And it trains the model based on the song data and the characteristics to output to generate a playlist. The theme is to go with the flow, right? So we started thinking of the flow of a song, but then we realized that it would be difficult to generate a song, especially since not much technology is there yet. And we also are limited by our computational power and, well, just general technology. So we decided we would instead play around with generating playlists and creating a playlist that flows well together. So how the model will work is it'll take in a few songs, it'll take a few songs. It'll generate values based on the pre-trained values, and it'll find songs that match those values and create a playlist using those songs.
Next up, first, in order to do anything with this, however, we need a data set. So for what our data set we did was we found a database online, a Spotify track analysis database, and it contained over 200,000 Spotify songs in it, sorted by their attributes and stuff. But unfortunately, due to time constraints and computational restrictions, we could only process 10,000 of these. And the way we actually got them is that we scraped the CSV, then we pulled them as MP3s, and then we had a script that converted those MP3s into a waveform audio format or .wav format. And those were later processed into a 32K bit rate and then converted into arrays. And those arrays of values we could actually feed into the neural network as input.
So one problem we encountered was that songs are really large. A song that's 200 seconds long with a 32 kilobits per second bitrate would have an array with over 6.4 million data, 6.4 million values. And training a model with thousands of songs with arrays that large would be time consuming and just not possible with our current technologies, or at least what we have access to. And it would not be viable either, because that much data would be very difficult to just find correlation in.
So we had a couple ideas starting out for how we fix this issue. First, we thought, well, maybe we decrease the bit rate to really, really small, 32K, bring it down to 2K. But that's still, millions of indices in the array that we're trying to put into the neural network. So that doesn't work. And then we thought, oh, maybe we just take a small chunk, like 5 seconds of the song at 2K bit rate. That's still way too much. And at that point, we're just not getting a song anymore. We're getting like maybe a beat or two. And we were pondering this for a little bit, and we eventually came across a Fourier transform for encoding MP3s. How this works is we take the MP3 and convert it to a WAV file. At that point, we run a Fourier transform on the WAV file. And just a little quick explanation, a Fourier transform breaks down a wave into the corresponding sine waves that add up to it. So each of these sine waves will have different amplitudes and different frequencies. And when you add them up, it creates this whole wave that can represent a song. So we broke it down into the sine waves that add up to it. And we looked at the sine waves with the 256 highest amplitude, and we looked at their frequencies. So the 256 highest amplitude sine waves that created this wave mean that these are the waves that are going to most represent the song. These are the ones that most affect what the actual resulting wave looks like. So we looked at these waves, we took their frequencies and used those frequencies as the inputs for the model. This means that we can cut down our song from 6.4 million inputs to a model to only 256 while still maintaining a lot of the actual, like what represents the song. So different songs will still look different. Yeah, so that takes us to the model. Now, the model, as I just talked about, has 256 inputs. There are 10 outputs, 10 values that we get out that represent what the song is. And we also used a leaky ReLU activation function because we tested a few and that worked the best. All outputs were also standardized to be between 0 and 10, and I'll talk about why later when I talk about training and accuracy. We had 3 hidden layers that started large, 512, 256, 128, 50. That's pretty standard. For optimization, we used the Atom optimizer, but we had an issue. When we were using the Atom optimizer, it kept just, the loss kept skyrocketing, just continuously. It just wouldn't stop. And what we realized is that the Atom optimizer actually has a small flaw. That's because it's really fast, but it can, if you have too big of a learning rate or too fast of a learning rate, it skyrockets the values. And so we decreased the learning rate down really small to 0.0001, and that fixed it. We also tried stochastic gradient descent, but the values were also too high, and when we fixed it, it was just worse than Atom, so we didn't use it. We trained it with 1024 epochs, and we also had a unique accuracy function. This accuracy function was essentially because we wanted 10 outputs and we wanted them to be as close to the inputs as possible. So what we did, we compared each actual output to the predicted output, and we took the difference. And if that difference was within 1.0, then we said that that was an accurate prediction and moved on. And this let us basically check if the 10 outputs were close enough. And we also used mean squared error for our loss function. And I'll hand it over to Jack.
All right. Just making sure, can you guys still hear me?
Yep.
All right, sounds good. So for the input on the playlist generation, we took the output of the neural network and just had a dictionary of songs. So just their title, artist, and then the corresponding characteristic array. And then for output was just the best songs for a playlist of a specified length. So for an example, we did 40 songs, and then we generated a playlist that was 10 songs long. But to make the playlist, we needed to compare any 2 songs. And for that, we came up with an error function that just compared the songs characteristic by characteristic. And it basically just found the difference in values, multiplied them by some weighting, and then took the square. And then that was the error for the 2 songs. And then to select the best playlist, we just iterated through songs, found the n-1 closest songs for a playlist of length n, summed up those errors, and then took the song with the lowest corresponding total error, and then its songs. Next slide, please. And then some other approaches that I attempted to try and make the error function a little more interesting was randomly weighting a characteristic heavier, which I hoped would create a theme for the playlist. Like you could get a very instrumental playlist or a very danceable playlist, but it really just made it way too random and genres kept jumping around everywhere. So that didn't work. I also tried randomly nudging the error just to maybe get a little more variety, but again, it just made it way too random. So some of the issues with it are that most of the time it's pretty good, but sometimes it fails, and when it fails pretty big. As you can see from the example, I don't think most people would put these 3 genres right next to each other in a playlist. And then possible improvements would be just continue to tweak the weightings for each characteristic, because I did that manually and I was never fully happy with it, partly because I got tired of listening to randomly generated songs. Another change would be to find the best playlist instead of a current approximation, but I couldn't find an efficient algorithm to go through all the possibilities, or at least quickly rule out poor possibilities.
Moving on to results of our project. So our model came out with a 56% accuracy rating, which based on what we have as our accuracy function is actually pretty good. So we have some categories obviously came out much better, such as speechiness and instrumentalness, with over a 90% accuracy rating. However, despite the percentages being lower, they're not that far off because they're within, like our accuracy function measures the distance between 0 to 10 of how far it is off. And what 50% accuracy rating means, like over half the values are close enough to where they can be they're close enough to being accurate to where the numbers aren't that representative. But when with the actual output of the algorithm, once we took the output of the neural network and put it into the algorithm, we were able to give it 40 songs and it would pick 10 songs out of them. And there was a cohesive element between them. So for example, we went with a more soft sound playlist. And there was that element of cohesion between all 10 that were in the output playlist. And we do have a lot of future plans for our project. First of all, we would love to give it more data and allow for a longer training time. That would obviously just increase the effectiveness of everything. We would also want to optimize the speed of the playlist generation. Right now, it isn't the quickest. As I mentioned before, we've run out of computation power and time. So we would like to optimize it. We would also like to check the songs against each other to ensure that the element of cohesion remains strong. And we would also like to have a possible integration with app APIs. So for example, we are creating Spotify playlists, but at the moment, we wanted to be able to integrate easily within the user's library once it's been generated. So we could, as a future addition, just add the Spotify API to it in order to just return it into the user's library upon generation.
Thank you for listening to our presentation. So our GitHub repository is the first link, and below that is our data set, which is from Kaggle, and it contains all the Spotify data.
Yes, that's something else we could do, but that I think, as I was testing, it would increase the time it would take exponentially, whereas there's other improvements that we could do that would not take exponential increase in time. Yeah. Yeah. Yes, that's specifically what we used. Yes.
Otherwise, it would have literally been incompletable.
Yeah.
Since no one's doing a standard Fourier transform.
Yeah.
We're not n squared design.
Yeah. Okay. Well, thank you so much.
All right. Good stuff. Hey, third group. How you guys doing? Is it done? Really? You shared it? Okay. Freeze the thing, pull it up. In the meantime, I'll try out some stand-up. Yeah. Quick update for you guys on the pizza. Safeway hates us. We have the pizza, don't worry. The pizza we got like an hour ago. It's probably still fine. Safeway apparently wanted like 10 pages of proof, and Semeka only sent us like the first page or something. I don't know. Safeway's a weird little place. They just don't really want us to have drinks today. So, yes. Did you finish something too? God bless you. Send it to Arnold Karn at UCSC. Here, I'll write it on the board in case anyone else wants to last minute something. All right. Cohen, hold the microphone. I don't know. You want to do stand up?
Is it being recorded? It's like, yeah, done, but don't screw up. Wait, what? Yes. No work. We'll see. I think it's 60 something.
Sorry, 60 slides? Gentlemen.
Oh no, those are all those are no.
Is it all hidden?
Those are templates.
It's just all hidden?
There's like when you download a template, you know how there's like all the
But
templates.
is
You
it
just never
hidden
delete
in
those. What?
Is it hidden? You guys
I can delete it right now.
We hold ourselves to the highest standards.
All right, they're gone. There are a lot of hidden slides though.
I believe it. I'm not getting a red sentence.
They're paying me.
Yeah.
Out of their pocket.
All right. I don't know what they have in store. I didn't have a chance to look at this. No, Cohen.
Wish you the best.
All right. Okay. All right. Same idea. Roughly 10 minutes for the presentation. Go through it. Answer questions.
Yeah.
Don't go overkill. Keep it simple.
Getting it.
Need to explain
Oh,
level of like pieces.
all right, don't worry. Can I get the remote or the presentation remote? Try it out for a sec.
Here down is to go to the next slide. Laser pointer.
Huh?
Just tap it.
Oh,
Oh, it's on like.
huh?
They're the one that choose who wins.
They get. You guys do get.
You'll see them. It goes to your right side.
Um.
Right, roughly 10 minutes. Keep in mind, also you guys probably want to scan things together.
All right. Hi, I am Ant.
I'm Tommy.
Okay, and we're our project was to create an efficient estimator for simulation. Okay. Wait, why isn't it working? Oh, it's not. No. There. Okay. So our problem is that chaotic simulations are a pain in the neck to predict. They take a lot of time. There's a lot of math involved. Nobody has time. Okay. So we thought, what if we could just use deep learning to predict these sort of simulations? So yeah. Oh, sorry about that. So that's pretty much our goal. So the question is that can we use an AI that or can we use an ML model to predict the result of a simulation by in some way mimicking it? Okay.
So our first goal was to replicate a simulation completely and accurately using an artificial intelligence agent. And our second goal was to have that agent use less time to predict a more accurate result compared to just running the simulation multiple times.
Oh, okay. So our methodology is pretty simple. We basically have two agents. We have a simulator, which is like a small game that we run a lot of times to get and to predict, say, and the average number of times a certain team would win. So it's basically like two teams fighting against each other. And then using these inputs and the prediction, we wanted to create a simplified version that can predict the simulation but faster. Okay, so this is our simulator was kind of inspired by games like chess and Stratego. So we randomly generate the board state using units represented by numbers from 1 to 5, and the team affiliation is represented by signs. Basically, what that means is, suppose you have a red team and a blue team. Red team will be all positive numbers, and blue team will be all negative numbers. So, and each unit has behaves very differently. So, for example, there's a tank unit. There's a sort of sneak unit, and there's range units, etc. Okay. So this is sort of a representation of what our board looks like, and each of these numbers will have one move. It'll move once, and then if it's close enough, it'll act on an enemy. So, for example, -3 will try to act on 3 if it moves first. And yeah. So -3 and +3 are the same unit type, and they move and interact in different ways. Some can move 2 steps at a time. Some can move 1 step at a time. Yeah. So our estimator is, well, first we tried using we used a feed-forward neural network with 3 linear layers, and we tried a bunch of activation functions such as ReLU and sigmoid. Then we also tried using a CNN with 2 conv2D layers and 3 linear layers. Now, talk about the other models.
Sure. So the linear regression thing is just from SCAI, and our custom model is where we just predict it by comparing the size of each team and just using a simple ratio to see who wins. Yeah. And this is what we got for our results. The CN, which resulted in our best result, was an MSC. We got an MSC of 0.00791. And our worst one was our custom model, which we expected since it was just, we didn't account for none of the units, like what they do. We just only compared team sizes. And yeah. As for the time, the feed 4 neural network performed the best with a time of 3.13 times 10 to the negative 4 seconds. And our custom one performed the worst. But overall, the CNN we were able to get a faster time than if we were to brute force it and just run the simulator multiple times. So
and for context, that's in log scaling. Okay, that's going from 10 to the negative 5 up to about 10 to the 4. So do keep that in mind. Oh. Yep.
Our limitations were we had lack of computation power and time. We tried using auto ML, but tried using ML in the beginning, but that didn't work. So we just stuck with our plan and tried implementing other models, but well, so, yeah.
All right. So as a tiny detail about the auto ML, I tried some techniques like auto PyTorch, which just would not load in, and auto gluon, which did not work well. Okay, so this doesn't exactly work with variable sized boards. So for example, if you give it, we trained with a 10 by 10 board, but it wouldn't work with a 30 by 30 board. So for that, we could use an RNN instead. Now we didn't test with multiple simulator types, so we could also try adding new units and different simulation types, basically. Yeah. And yeah.
With meticulous effort, I think, and ingenuity, we were able to develop a highly effective model that accurately predicts board state outcomes. The solutions, why is it aerodynamic? The solutions are very aerodynamic. And
if I may, okay. So we can this is basically what this is just a proof of concept that we can extend the idea of simulating things with neural networks to far more complex simulations. Where, for example, if we worked in aerodynamics. So we also thought about trying to make this into a search problem, thinking about where we would place units so that we are guaranteed to win as many times as possible, or get the highest win probability. And those are our references. Thank you. Yes.
Go back to the time slide. I was wondering, this times the training time, or is it just how long it took to predict accuracy?
It's the time it took to predict.
And why are we using that as a
the time it took to train isn't really important here, because what our end goal is is that at the end it should be able to predict quickly. Training time doesn't matter. We train once and it'll work. That's it. Yeah.
Modeling simulations, specifically aerodynamic simulations with a neural network already exist in GINNs?
Yes. What?
This works for some very simple systems. How it's like organic systems like that. Like last one is like, how would this work on that all times are?
I'm not sure. I'll get back to you on that. It is a proof of concept.
Actually, on your results slide, this is for this is a mean squared error type of thing.
Yeah.
How does this compare against the simulation? Because you just show, like, in terms of accuracy, you don't have any evaluations there. You have just simulator execution time, but then you don't have any sort of.
Because the simulator would be 100%, because that's our input and that's our output.
Bring your results to the simulator. Like, in terms of like measuring correlation relative results.
Yeah.
Pretty sure to understand. Well, listen to the presentation. My understanding is that the simulator is the ground truth. And that the estimator is attempting to replicate that ground truth so that mean squared error, which represents the difference in probability from the actual run from the actual simulation. So that's why there's no simulation RMSE, because that's the ground truth. So technically you could say that's 0. Right. You compare it against it.
Yeah, I understand.
Any other questions? Yes.
Can you interpret these results? Because I see a number 0.0079. That means absolutely nothing. Put some context.
Okay, so basically, what that means is, so if you take that, that means that compared to the actual simulator, it's really, really close. That's all. That's what it means. It's around you.
In the context of what we're trying to predict, what is the RMSE supposed to represent? Is it taking how inaccurate and how we measure it?
RMSE is just how basically how close we are to the actual ground truth.
All right. Any last questions? Cool. Thank you guys so much. Thanks, Cohen. Really big presentation on your part. He wasn't involved. Ladies and gentlemen, he was not involved. His name isn't on the slides. Christ on a bike. Okay. Here's the deal. As you guys can all probably very simply see, the food is here. So I'll ask a quick question. Do we want to do the last presentation before we do food, or are we gonna? Yes. Did you send it? Excellent. To that email. Excellent. Yep. All right. Rosen. Good stuff. Give me a sec.
Also, I'm pretty sure that's MSC. I'm pretty sure it's MSC. It's not MSC. I don't know, you guys. I'd have to go relook at the paper results. I'm pretty sure on the paper we put MSC. Okay, that can fix. And then like convert it to RMSE. Is there another group presenting? What? Oh, Lino.
Terrain.
We so you just did that just now.
Just the slides, I guess. All right. You have 17 slides. You think you can do this in like 10 minutes? You have like 17 slides. You think you can do this in 10 minutes?
Yeah.
Did you do this whole thing from scratch, or did you just?
No. I had this project. I just made a slideshow while you guys.
Does it fit the theme? Yeah.
It's not.
Yeah, we'll see. I could do.
Thank you.
Previous project.
Oh. Yeah, you're getting money.
Is there like a clicker or something?
Go. Down is down.
Okay. Perfect.
All right. Hi, children. We're back again. Hope you didn't lose your attention in that momentary break. We have one last final presentation here. It sounds interesting. I see GPT in it, which makes me excited. So I'm gonna pass this off to Lino. He seems to know what he's doing. Again, 10 minutes to get the idea. All righty, and then food. Actually, voting, then food. I'm gonna work on that.
Hey everyone, I'm Lena Levan, and this is research I've been doing for a personal project, not for this. So the slides are a little bit hastily put together. Sorry about that. But I think there's definitely some promise here, so I'm excited to talk about it. So the title of this paper that I'm writing, but also this slideshow, is Terrain GPT, a practical approach to ML-based terrain generation for real-time games, which is a mouthful, but I think it makes sense. So here's the problem motivation. So terrain generation is a super valuable tool for building immersive video games. But the problem is building large and realistic terrain is difficult and it's very expensive. It's really expensive. Trust me, like it takes a lot of work. So the current generation of terrain generation tools have to choose between looking good and being fast, which is never a trade-off you want to do. So yeah. So this is related to the theme. I mean, it's slightly related to the theme in that current models, especially AI models, which is what we were focusing on in this presentation, are awful at going with the flow of terrain. I'll talk about more on this later, but just have faith. We'll cover this. All right, so let's talk about state of the art. So there are three main techniques that are used in state of the art right now that are not machine learning, just in general. So number one, everyone's heard of this, is noise functions. By far the most common technique. Every video game you've heard of uses it. So that's Minecraft, No Man's Sky, everything. Like if you Rust, like whatever. Name a video game that has procedural terrain, it uses noise. So there's a few good papers on this, but the fundamental limitation is that noise functions can only really approximate noise, and you can do some tricks to make the human brain think it looks like terrain, but because it's genuinely based on nothing outside of just, maybe changing some parameters around until it looks good to an artist, there's a lot of limitations around, hey, what if I want to make this style of terrain or this style of terrain? You have to make different noise functions and different generators for every style of terrain. And it doesn't really generalize super well. And also the results don't look great. I wish I had an evaluation slide here. So the second technique that's used, and this is more for like movie production, is erosion simulation. So generally they start off with like a base of noise terrain, and then they run 10,000 years of erosion simulation on it, and then eventually it starts looking really good. Problem is, that is way too slow for real-time games. And so if you've seen Dune, Mandalorian, everything like that, this is the technique they use. There's the industry standard is called TerraGen. It's software for doing that, and it allows you to control some parameters. But at the end of the day, it still just is noise generation, but with another layer on top to make it at least somewhat physically based. So the third one, which is actually, I'm surprised to say, underutilized, is AI generated terrain. It's very rare. There's a few papers I found out there. It's fast, which is exactly what we're looking for in real-time games. It looks good. There are lots of practical issues with using them right now. And so that's one example of prior in the field. So my contribution is that all previous attempts at AI generated terrain have used GANs, which are great for building a proof of concept 5 years ago, and not super great when nowadays we have models that perform way better and train faster and generate faster. So state of the art nowadays is transformers, and no one has applied a transformer model to terrain generation. So the other contribution is making AI generated terrain practical by allowing terrain to be tiled. In the past, AI generated terrain have been able to make some like squares of terrain, which is cool if you have a really small scene and that's it, and you don't want to generate anything more. But that's like never the case for anything. So I wasn't really convinced what the use case was, but we can do better. So how? Okay, so this is the solution. The big thing is just noticing how other games do it, like real-time games do it, and then just interpret that in an AI style. So we actually have 5 separate models that we switch out for each case. So the base case is you have no terrain and you just need to generate some base. So that one will genuinely just generate some amount of terrain. And then you need 4 models depending on the cases of what terrain do you have around. So if you have one tile next to you, you have to generate that boundary line, but the rest of the terrain can be however you want. So we have 5 models total. 4 of them are for the different conditions on how many neighbors do you have, basically. So the data set. So USGS, the US Geographical Survey, publicly is a height map of 30% of the US, which is extracted through a little bit of satellite data, and it's also manual, like someone going over there and scanning it with LiDAR. So that's why it's not 100%, which is fair. Each tile is about 0.5 degrees of the radius of the Earth, which is a lot, which is unfortunate because I was hoping for more fine-grained, but that's like a future work thing. That's spoilers. Hold on. Okay, so all images in the data set are 2K. Unfortunately, the computer I was training this on cannot do that. So we're not doing that. I downscaled all of them to 256 first. I think I downloaded around 10,000 images for this specific thing. So there's a lot of good articles actually online on how you can do this. So I just picked one up and just did it. I ran through it. And it turns out that you can just use standard image generation with transformers exactly the same way, assuming you don't have the tiling stuff. The tiling stuff is a little more complicated, but essentially, if you look at this diagram, you just need to add another linear embedding, and then it's exactly the same, or up to 4, I guess, other linear embeddings. Yeah. Okay, so evaluation. So here are some images I generated off the thing. So a few things. One, these are cherry picked. These are the best I could find off the model. So I probably ran it about 10, 20 times to get these. And as you can see, they look okay. It would be cool to see them on real terrain, and hopefully that's a future work thing. And also notice how they're not tiled. Ha! Yeah, so in all honesty, I didn't get around to training the other 4 models, which leads us into future work. So a few ideas that you can do. Transformer models allow you to do good like text input as well as like arbitrary inputs, basically. So I think it'd be cool if you could define a theme for the terrain, like you could do a mountain range or like Badlands or whatever. Pick a style of terrain, and you could generate it based on that, which would be super powerful for artists working on this kind of stuff. Another thing is that there's actually no metric for evaluating results in terrain generation. Like there's nothing that says this is a better result than this result. So I'm thinking maybe you could do like a GAN or something, and then use that as a standard and publish the weights and say that this is how much better we are compared to previous techniques. And also, we want to implement this in a latency sensitive scenario. Right now, it's just a proof of demo Python little file that you can run and generate terrain, but ideally, this would be implemented in a game to prove that it works in that scenario. And also a higher resolution height map, 256 by 256, especially at that scale, is a no-go for this sort of thing. But maybe it would look cool from like an infinite map generating thing or something. Yeah, that's my presentation. Thank you.
Any questions? Nice. Oh, we got.
Yes.
Never mind.
Yes.
AI generation.
I think they announced they're doing something with that. I haven't tried it myself, to be honest. So this may be just like the thing, and I just am too slow. But I'm sure that this isn't like a completely new concept. Yes. Yes. Wave function collapse is too slow to run on classical computers, especially at the scale of terrain generation, especially when you need to do big terrain generation. So cool algorithm, works really well on small scale, doesn't scale up, unfortunately. Anyone else have any questions or just comments in general? Cool. Thank you.
Thank you very much. Okay. It is that time. Before we have food, we're going to figure out the vote for this. So here's what's going to happen. Cohen is going to send the form. We made it into a tiny URL, so it looks nice. We'll probably also write it on the board, so it's easy for you guys in the Sky's No Limit channel of the Discord server. So open that up. There is going to be a Google form. We'll pull it up on the screen here probably as well. There is going to be 4 options for rankings: first, second, third, and fourth. Each project can only be in one of them, or I will make sure your vote doesn't count personally. So yeah, I'll strike it from the record. So yeah, once all those are in, we'll tabulate, we'll announce the winners, we'll have food, we'll have a great old time, and that'll be basically it. And then, I don't know. We also have another form for like feedback and stuff, but that'll be closer to the end. Cool beans. Cohen, have you sent that in already?
Yeah.
Excellent. It is in the, what is the thing? It is in the Sky is No Limit channel on the Discord server. And then Cohen will probably pull it up. This is in, no, it's not. It's in, what is this one? Oh, there it is. Yeah, look at that.
This is the same thing.
You can put it in. It'll probably balance out. But the thing is, I'm just going to say, this isn't really something I can properly enforce. If everyone who voted, if everyone who made a project put their own project in first, it wouldn't balance out. We'll go in the honor system here. Kindly put your own project as fourth. I can't really enforce this in any way, but they're scoring out. Would it balance out in the other direction? It would. That's a good point.
Yes.
Just rank it. Yeah, just be honest.
Question from Zoom. Is there any way that I could access it from a non-Santa Cruz account?
1 second, let me fix this for you. One
Thank
moment, please. Would I?
I can just give you my email
on, give
too
me a
if
sec.
that works.
Give me a sec, give me a sec, give me a sec, give me a sec. Don't do that. Give me a second. Hold on. Responses. Oh shoot. I forgot one other thing. Now it's correct. I think this should work now. Wait, that's the wrong thing. Oh God, hold this cone. I'm going to reset the form.
Really?
Give me a sec.
He could just send them
Nope, give me a sec. There's something else that's problematic.
What happened?
I don't know.
Don't worry about it.
After voting.
Once everyone's done,
After winning
and
time.
we decide.
Oh wait, there's the form. Do you agree that you do not exist?
What?
For the context of the project.
All right, hold on.
I didn't have anything to do with the project.
One response.
Why are you on it? I don't know. I don't know. Maybe there's someone else here. I don't know.
Okay. Where's that mic? Try it now. Does it work for you to send a response to this now?
Yeah, thank you.
Absolutely. No need to reset. Look at me go, guys. Technological whiz, thinking on my feet. I forgot that all of our old forms have been set to only allow people from Santa Cruz. You were able to go in it before.
And sorry, I didn't.
Yeah, you were able to
hear-
vote before. We had like 8 responses.
I didn't hear how we should vote for ourselves.
Not yet. We're going to announce the winners first.
No, how should we vote for ourselves? Like,
Sorry, say that again.
how should we vote for ourselves? I heard several different things.
Just vote honestly.
Okay.
We have no way of enforcing this. It's the same thing as before.
This is just discrimination.
You got the food.
He's like, oh yeah, we're gonna be good. They get the food first.
No.
Authors get it last.
No.
And I point to Dylan
I
getting
don't
food
care.
already. You know, I thought it was like the.
All right. How's it going, guys? How's the voting? Because right now I think we have a total of 14 responses, which is pretty cool. Just once. I think you should only be able to vote once. No, nothing changed. I just opened it up. That's it. I think you're only allowed to vote once. All right. And we are going to do the exact same scoring algorithm as last time. If you guys have something better to suggest, then be my guest because you don't know the results. This is the algorithm. Basically, what I wanted to do was rank choice, but I can't do rank choice because that takes work. So the idea is basically reverse quantify the ranking of each vote. So a vote in first is 4 points and a vote in fourth is 1 point. Yeah, it's pretty easy. So we're just doing that. I've done it before. It'll work again. As a plugin, I looked last time we did this. I wasn't able to find one. I would love that. I really would. All right. 16 responses. Is that everyone or everyone who is interested in voting? Actually, quickly, give me a thumbs up if you ever vote in. Huh? Have. If you're good. If you have it in, voting. All good? Everyone's voted who's voting. Nice. All right. Time to do some math. Give me a sec, guys.
When you it's a UCSC, but it's Berkeley, LA, San Diego, all these schools. We don't want so UCSD now on your own. You gotta be like, okay, we're interested. They're like, yeah, let me get started. I think it's a little lot. You guys can join if you have. So what's gonna happen is like sending them the presentation. I'll reduce this. Well, no, the 11 is basically one that means I'm the
Yeah, no, of course. I was curious how it was all started. So the professor, I do. Yes. Like just put it. No, I think yeah, absolutely. Just like whatever you want. I don't know if it's like that. I think we just kind of keep it up. Like I think at least I don't know. 100. Yeah. Yeah, I talked with the getting in someone. Program management. Someone asked if failed out today. I guess I had to pull myself together. When this guy was like, I bet he was getting their texts. That's yeah, I don't want it to get any. Yeah, I'm doing it. It's really nice. I'm literally talking. No peeking, Howard. Howard, no peeking. Yeah, you didn't land, my bad.
Oh.
Oh my goodness. AI jobs. Oh, I remember that. Yeah, I think they announced I'm gonna put an announcement out about that. Oh, that's what's yeah, it's the prize money. Guess what? Yeah, I'm 11 months old. Oh, yeah, so how much was it first? It's 2x, so you see. Go to SCAI's
I'll tell that.
Okay. What's my?
We have the votes, and that means we will soon have food. Everything's tabulated. All right. How do we prefer that I do this? Do we go from fourth to first for suspense? Fourth to first? Fourth, third, and first. That's a very good point because that's implied. Alrighty. So in fourth place with a combined score of 22 points based off my silly little tabulation algorithm is the simulation estimation thingy. Yeah, good stuff. Congrats, guys. Really cool. Top 4 is really good, honestly. You're getting money for that. I don't remember the exact score. I think it's $150 divided between you guys, which is pretty good for fourth place. Yeah. Third place. Third place is with 41 points is the Spike Neural Networks. Very well done. Very, very well done. I don't remember what 200? 200. Wait. Oh yeah, 2x thing. Right. So it's $200 for you guys. Very well done. All right. Big shout out for first with a grand total of $550 for the first place team or project. It doesn't really matter. All right. In first place with 53 points is the playlist generation algorithm. Congratulations, guys. Very, very deserved. And then with 44 points in second place, so close between second and third, is Terrain GPT. Very, very cool. It might take a while for the actual splits to go through because Sameka hates us and doesn't really like giving us money when we need it. It's still not in. It will be soon. It's coming. It's been tabulating.
I promise we'll have that.
I hate them as much as you do, probably more. But yeah, thank you guys. It's been an excellent competition. Yes, and then also, before we get food, or I don't know, at some point, we're going to be sending a feedback form for you guys to fill out, just for general input on how we did this year, what you might want to see next year, more competitions, less competitions. However, we'll be sending that soon, so check Discord, I think. Cohen, have you sent that yet, or? You'll send it soon. Feedback form. Yeah, that'll be sent out soon. We'll really appreciate it if whoever came to any meeting whatsoever gives us advice, how they think it went, what they'd like to see improved, what they might want to see in terms of topics next year. We've already covered a lot of models. We're going to do a lot of the same probably because there's going to be new people, but we want to cover new things as well. So give us some input. We'd love to see some new stuff. Best place to do that is on the forum because we'll be able to hear every single person's opinion that way. So thank you guys again. Enjoy the rest of the celebrations. We'll be here if you guys want to talk, have food, chill. It's gonna be fun. And thank you guys again. It's been great. You can't find the form. It's in All right. I don't know. Form an orderly queue and we'll figure out how we divide food.
You don't.
What does that mean?
Yeah.
I did. Over there, like, yeah, it's like 5 questions long. It's not anything super intensive, but we'll really appreciate it if you guys fill that out.